is points of concurrency. So basically for this lesson, what we are going to be doing is using our constructions to talk about where different constructions intersect and what that intersection point is called. So to start, we're going to construct the perpendicular bisector of side AB and then the perpendicular bisector of side AC. So to do that, we're going to use endpoint A, open up more than halfway, go above and below. And what's interesting now that's actually going to be happening is that your arcs are going to be big as well as possibly cross, and you have to kind of stay organized in terms of what you're looking for in terms of the intersection. So I'm going to go ahead, connect through my arcs, and put some arrows on the ends to show that this is the perpendicular bisector. Excellent, here to here. So that's for AB. And now we need for AC. So this is when we have to stay a little organized, go from C, have an arc above, have an arc below. I'm going to go to endpoint A here, here. Oops, I have to go back to C now. It wasn't long enough. Turn this. Excellent. And now go through sections, little arrows on the end, perpendicular bisector. And there you have it. Okay, so basically now I have my two perpendicular bisectors. So here's the midpoint of this side, here's the midpoint of this side. I also formed right angles. Now here's the question. What do you think is going to happen if we constructed the perpendicular bisector of side CB here? If I do this construction again, what do you think is going to happen? And what we know is actually going to happen is if we did the perpendicular bisector of side CB, it would intersect through point, and we'll call it point D. It's going to actually intersect through this point right here, and I'll label it point D. So if I did the perpendicular bisector, it's going to go through point D. So let's actually show you what that's going to look like. And it would look like something like this. So it would intersect, here's the arc marks, through the same point right here. So here in red is the perpendicular bisector of AB, blue is the perpendicular bisector of AC, and green is the perpendicular bisector of CB. When all three perpendicular bisectors intersect, it's called a point of concurrency. So it's the point at which they intersect. That specific point is called the circumcenter. Okay, so this point here, this point that I marked where all three intersect is called the circumcenter. Now the cool thing is that when you find the circumcenter, you don't have to do all three perpendicular bisectors because it's understood that the third one is always going to intersect where the first two do. Okay, so what is the circumcenter? I know how to find it by doing the perpendicular bisectors of two sides of the triangle. But what is the circumcenter? So the circumcenter is actually the center of the circle that is circumscribed about the triangle. So now circumscribed is a new term that we haven't really discussed yet. So what it means to have a circle that's circumscribed about the triangle means that it goes around the triangle or like the outside, but it must be touching. So it's kind of like when we talk about it being inscribed and going on the inside and touching. If it's circumscribed, it's going around the outside and it's touching. So how do I actually get that circle now? Take a look. I can now construct a circle with a center P, and I'm going to go to C. So I'm going to take my compass, put the center on P, and stretch out to C. And let's get this circle like this. And I can now, oops, swing my circle. And look what happens. C is on the circle, B is on the circle, and A is on the circle. So let's think about this. If A is on the circle, C is on the circle, and B is on the circle, then why could I say this over here? Why could I come up with this conclusion? Now, these three dots signify therefore. So if you see this three dots, it actually means therefore. So based on that, the circumcenter is the center of the circle that is circumscribed about the triangle. Why can I say that AP, BP, and CP are equal? And for that, I'm actually going to draw in from A to P, B to P, and C to P. And what do you notice they all are? Well, they're all the radii of the same circle. They're all the radii of circle P. So let's write that here. So why are they all equal? They are all the radii of the same circle. In this case, circle P. So we talked about that in one of the beginning lessons, that the radii in the same circle are all equal. So here's a perfect example of that right here. Okay, so what should you be taking away? The perpendicular bisectors intersect in the triangle at the point called the circumcenter, and then you then get the center of the circle that's going to be circumscribed about that triangle. Okay, next we're going to deal with, not this, we're going to deal with angle bisectors. So we're going to construct the angle bisector of angle A and then angle B. So angle bisector construction, open up your compass, needle on the vertex, swing an arc so that it goes through both sides of the angle. You get 2 points of intersection. Take your compass now. You're going to swing 2 more arcs that are the same size from both points of intersection. There you go. And then you connect. So we're going to go from vertex A through the point of intersection of those arcs. There you go. Let's do the same thing from B now. So I'm going to take this color, go to B. All right, so I'm going to swing through B. Point of intersection here and here. So 2 more arcs from those points. Have an arc here. An arc here. Connect from B to the point of intersection. Okay, now super similar. These 2 angle bisectors intersect at this point right here. And again, let's just label this point D. So if I do the angle bisector from C, what do you think is going to be true? And again, similar to the perpendicular bisector, it's going to go through that point of intersection labeled D. So we don't actually have to construct the angle bisector here. What we can say now is that we know it would go through point D. Right, so let's see what it looks like when it's actually done. Here it is. So you have the blue coming from A, that's the angle bisector of angle A. The green is the angle bisector of angle C, and the red is the angle bisector of angle B, excuse me. So now we know, what is it called when all the angle bisectors intersect? And it's actually called the incenter. So the incenter would be this point right here, point D. So point D is the incenter. So what is the incenter? Well, the incenter is the center of the circle that is inscribed in the triangle. So that kind of means if I could fit a triangle, if I could fit a circle right here, perfectly inside of this triangle, D is the center of that circle. Now here's the thing. You can't just take your compass and go from here to here like you did for the circle that was circumscribed about the triangle. There's an extra step now. When you're dealing with the incenter, you must construct the line perpendicular from the incenter to one side of the triangle to get the radius of that circle. So remember when we did a line perpendicular from a point not on a line? Well, that's the construction we need to do here. So I'm going to form a line that's perpendicular to AC, but goes through D. So to do that, I need to start first with that smiley face. I'm going to put my needle right on D, and I'm going to swing a smiley face that goes through side AC, as so. Now to get my line perpendicular, I'm going to take this, go to each point of intersection, extend my page a little, and I'm going to swing an arc underneath, as so, and then go to the other point of intersection. And now, since this is just a point to get, I did this construction just to get an intersection point, I'm going to go from D through there. Now notice, this point of intersection is different from where the red line crosses AC. So now your new radius, the radius of the circle that's going to be inscribed inside of this triangle, is going to go from here to here. So from D to this new point right here. That's going to be the radius. You know what? Let's actually label this E. And then let's put a little note over here. DE is the radius of the circle inscribed in the triangle. Okay, so that we have a little note and you know where we're getting that radius from. All right, so now we can actually do our circle. I'm going to go from D to E. I'm going to change the color. Now I can make my nice circle. Bam. Oh, it's a little bit off. Hold on one second. I didn't open this up far enough. All right, this should be a little bit more like this, let's see. And there it is. Okay, so notice here it's a little bit off. That's okay. We kind of take into account that right here the lines aren't intersecting perfectly, but you get the idea. So now the circle is inscribed inside of this triangle. It has a radius of DE, and it fits perfectly inside of that triangle right there. Okay, and remember we did here, in order to get this line here, we did a smiley face, and then we did the perpendicular bisector. Okay, so now let's try to figure out how could we find the midpoint of a side and then connect the midpoint to its opposite vertex C. And we're doing this for a very specific reason, because these two steps together actually form a specific segment. Okay, so first let's find the midpoint of side AB, and we're going to do that by doing the perpendicular bisector construction. Let's go from A to B and do the perpendicular bisector. So open up here to here, swing an arc above and below, flip, go to B, above, below, connect the line through the intersections, put an arrow at the end, and now let's put a point right here, and then that's going to be your midpoint. So I'm going to type in midpoint. Okay, so you found the midpoint. Now we have to connect the midpoint to the opposite vertex. So its opposite vertex means what's the angle essentially of the triangle that's not on AB, and that's C. So when we connect from the midpoint to C, I'm going to make this yellow. This new segment that we just created has a special name. And this new segment is actually known as a median. So when you connect the midpoint to the opposite vertex, it's known as a median. I'm going to type here, median. Okay. So here's your median, and then there's your midpoint. Now we're going to do the same thing for side BC. So So now I'm going to go from B to C, do the perpendicular bisector to get the midpoint, and then connect the midpoint to its opposite vertex. So here, and then above. Now, you see how there's so many things that are intersecting? This is when you have to kind of be careful in terms of keeping track of what arcs matter. Then we connect. Draw some arrows. Here's your midpoint. Now A is your opposite vertex. So let's kind of just have our midpoint. Here's your midpoint. And now we're going to connect from this midpoint to the opposite vertex, which is A. So from here to here, and I'm going to actually highlight this like I did with the yellow. Make this purple. Now that purple segment is your median. So this is when it gets very tricky because you have your medians intersecting right here, and you have your perpendicular bisectors intersecting here, and you have all these other things intersecting here. So the point that we're really looking for, the point that's important right now, is the point of intersection of just the median. So this point right here in red. So now, whenever your medians intersect, the point of concurrency of your medians, that point is called the centroid. So when all three of your medians, really you only need two to intersect. When they intersect, that point right there is called the centroid. Now remember, a median is the segment drawn from the vertex to the midpoint of its opposite side. In order to do the median, in order to actually get the median, you have to do a perpendicular bisector construction first, right? So there's all these crazy things that kind of come into play when you have a median. Now, personally, I like the centroid the most out of all the points of concurrency because to me, the centroid is the most interesting. The centroid does a lot of things. Okay, so actually, I think this is a little bit down here, sorry. The first thing that the centroid does, it's the point where all three medians intersect, obviously. It's also the center of gravity of that triangle. So it's almost like you could think of kind of putting the triangle on your pointer finger at the centroid, and it would be perfectly balanced. The next thing that I think is kind of cool is that the centroid is the average of all the vertices, right? So it's the average of the vertices. Now, this only applies when we're talking about things that are on the coordinate plane. Meaning, when we do a construction right now, there's no coordinate plane, right? We don't see any graph. But once we get to working with a coordinate plane, like a piece of graph paper, which we do have an example of, you think of average with the vertices, and that's how you can find the centroid. So let's actually take a look at how that would work. So if the centroid is the average of the vertices, and we have this triangle below with A, B, and C, we want to find the coordinates of the centroid. So remember what we said. It's the average, right? So how do you find average? And the way you find average is by you add the number of values up and you divide by that number. So let's put over here. So in order to find the centroid, it's going to be a coordinate. It's going to be the average of your x values and then your average of your y values. So essentially, if I have to find the average of the x's, well, let's write down our 3 points. What 3 points do we have? We have A, which is 7, 9. We have B, which is 3, 3. And then we have C, which is 11, 3. Okay, so let's highlight or let's kind of circle our x's and our y's. So our x values are these values right here. And then your y values are these values right here. So to find the average, we would add up our 3 x values, which is 7, 3, and 11. And we would divide by the number of values that you added up, which was 3. Okay? To get the average of the y's, you would add up your 3 values, 9, 3, and 3, and you divide by 1, 2, 3. And remember, this is a coordinate, so it has to be put in a set of parentheses. Okay, so what do we get? We get 14 and 7, so that's 21 divided by 3. And then we have 15 divided by 3. Oh, sorry, it's a little crazy with my handwriting. Then we end up with 7, comma 5. Perfect. So now let's see if this makes sense. Let's plot the point 7, 5. This is 3, 4, 5, 6, 7. Now, does this look to be the center of the triangle? And yeah, it does. So we know that the average of those 3 vertices is the centroid, which is the point 7, comma 5. That's one way that you can use the centroid in this instance. Now, here's another thing that the centroid does that we didn't put on the list, but it's actually really, really important, and it really does deserve its own slide. This is key. The centroid divides each median into a 2-to-1 ratio. So the median is divided into a 2-to-1 ratio. And if you don't know what a ratio is, I think of like ratios in terms of baking. So like for every 1 cup of flour, say you need 2 cups of sugar, right? So for every 1 cup of flour, you need 2 cups of sugar. So if you have 2 cups of flour, you should have 4 cups of sugar. Here's an example, and let's see if we can kind of figure this out. A 2-to-1 ratio. So it kind of means that the first part is 2 times as big as the second part, right? So let's see here. It says that we have medians AD, EB, and CF. So all the segments that are drawn in are the medians, and they intersect at G. So where the medians intersect, that means that G is a centroid. Put that here. G is the centroid. Okay. So since G is the centroid, that means that G divides AD, EB, and CF into a 2-to-1 ratio. Okay? So now FG is 12. So let's take a look. From F to G, so from here to here, is 12. Okay. So I'm going to highlight our first key piece of information. FG is part of this median, which is CF right here. So CF is a median. Right? And that means that G is the centroid. That means that G divides CF into a 2-to-1 ratio. All right, so let's look at this here. That means that CG is 2 times as big as GF. So CG is 2 times as big as GF. So I kind of think of this as this piece is 2 times as big as this piece. So if you know that GF is 12 and this is 2 times as big as 12, then what is from G to C? So think about it. 12 times 2 gives you 24. So GC has to be 24. So now this, I know, GC, 24. And you can actually compare the two. If you do 24 to 12 and you write it as a ratio, right? Both pieces can be divided by 2, and then you end up with 12 to 6. Divide those 2 pieces by 2, or even bigger, you divide them by 3. And if you divide both by 3, you get 4 to 2. Divide that again, and you actually get 2 to 1. Right, so 24 to 12 does eventually reduce down to a 2-to-1 ratio. right? All of these, right, 2 and 4. 4 is twice as big as 2. 12 is twice as big as 6. They all reduce down to a 2-to-1 ratio. So the length of GC is 24. Now, something else that's interesting is they could also ask for the length from F to C, right? And F to C would just be 12 plus 12 plus 24, which is 36. They could ask for that too. If I'm just going to throw in a number quickly, suppose I tell you that GE is, I don't know, 8. If GE is 8, then what would be BG? If this is 8, what would this be? Hopefully you're thinking, well, then this is half the length of GE, so it should then be 4. Okay, so that's kind of how something like this works. Okay. We will do a little bit more of this as we go on, but again, a 2-to-1 ratio, this is kind of what we're talking about. And then finally, we have something like this. Again, dealing with centroids and asking to find true statements. So again, we have our 3 medians, SC, KE, LR, and M is then the centroid. So each of these are divided into 2-to-1 ratio. We want to know which statement must always be true. So think about what you know, right? There's that 2-to-1 ratio, and we're going to go through it. So this says 3 times MC would give you SC, okay? RM is equal to 2 times MC. MC is equal to 1/3 of SM, and then SM is equal to KM. Okay, so looking at all of these, the only thing that we know is true with the centroid or medians is that we have to be talking about the same median. So if you look here where it says SM and KM, this can't be true because we can't compare different medians within this triangle. The same thing here with choice 3. RM and 2 times MC, they're not along the same median, so that's not true. But here, these are 2 statements that we kind of have to think about. Now, here's MC. So I'm actually going to use my compass to help me out just to kind of think about this. Now, it's a 2-to-1 ratio, right? So this is twice as big as this is here. So if I have the length of MC, there's 2 more of these lengths here and here that make up SM, right? So let's actually see. If I take MC, how many MCs are along this whole thing? So we have 1, okay. Then we have 2. And then we have, I moved it a little bit. And then we have 3. So we can kind of think of this as really 3 lengths of MC or CM make up SC. So although it's a 2-to-1 ratio, there are 3 parts, right? So a 2-to-1 ratio, put this over here, right? A 2-to-1 ratio creates 3 parts along the median, right? You have 1, 2, 3. Really 3 equal parts along the median. All right, so let's see. Oh, that's actually what choice 1 says. 3 MCs gives you SC, so we know it has to be choice 1. It's not choice 2 because MC is 1/3 of SC, not SM. The SC, so that's why that's not correct. Okay, so that's that here. All right, now let's talk about our last point of concurrency, and it's going to be dealing with the altitudes of a triangle. So we just have to go through what an altitude represents, and the altitude actually represents the height of a triangle. So I think of like when you go on an airplane, if you've ever been, they say, you know, we reach an altitude of, I don't know, 22 or 2,200 feet. You can now turn on your electronic devices. They're talking about the height of the plane in the sky. If you go to the doctor and they ask you to take your height, they want to see how tall you are. They ask you to stand straight up and down. They're asking you to stand perpendicular to the ground. Right? So the altitude is the height of the triangle. It must be perpendicular to the opposite side. So it's going to go from the vertex and be perpendicular to the opposite side. That means you have to create a perpendicular line from a point not on the line. So if we're going to create the altitude here, I'm going to create a line perpendicular to AC from point B. So that's your smiley face construction and then the perpendicular bisector of the points of intersection. So to do that, take my compass, I'm going to go from B, go past AC, as so, swing and swing. I get 2 points of intersection here and here. Take my compass, swing an arc only below since I have my point above. Flip it around, go to the other point of intersection, swing my other arc, and now I'm going to connect from B through, put a little arrow on the end, and put a little right angle. So now the altitude is actually the piece that goes from this point here to this point right here. I'm going to label this point, point E. So the altitude is segment BC. So right here, this is the altitude. I should type in. So this is your altitude right here from B to E. Okay. Now, obviously, we talked about points of concurrency, and we know however we do in your altitudes, they're always going to intersect. Now, the difference is for the altitudes, the point of concurrency is called the orthocenter. The difference is with the orthocenter, it can intersect in different places in terms of a triangle. So take a look. When you have a right triangle and you construct all the altitudes, the point of concurrency, the orthocenter, actually ends up on the right angle right here. It ends up on the triangle. When you have an obtuse triangle, it ends up outside. When you have an acute triangle, it ends up inside. So the point of concurrency can change. So when it's a right triangle, the point of concurrency is on the right angle. When you have an obtuse triangle, point of concurrency is outside triangle. And when you have an acute triangle, the point of concurrency is inside. And that really finishes up all the points of concurrency. So just to go through quickly, what we did was first, when you have the point of concurrency for the perpendicular bisectors, that's called the circumcenter. The point of concurrency for all the angle bisectors is called the incenter. The point of concurrency for the medians is called the centroid. And the point of concurrency for the altitudes is called the orthocenter. If you have any questions with this lesson, feel free to email us or to comment in our Google Classroom.